Okay, great. So, I'd also like to start by thanking the organizers for inviting me and yeah, letting me talk in this very nice conference. And so also apologies, I think my topic might be a little bit the most esoteric one of them all, but I hope you will still enjoy it. So yeah, so I'm going to talk about this sort of spectral asymptotics for noisy non-selfadjoint operators, which has been now done in sort of collaboration with a couple of guys. So recently also Anirban Bazak and Ofer Zaitouni, which are both more probabilists, and a little bit older with Stefan Nonmacher and Johannes Shestran. So let's maybe just jump in, and maybe let me say at the beginning, so if anybody has any questions, please just switch on your mic and ask them. I realize it's a bit maybe a mixed crowd, so if anything is unclear or you have a comment, just go ahead and ask or put it in a comment. I can't see the comments, but hopefully somebody has an eye on it. So maybe to start out, why do we study, or why we're interested in the spectra of non-selfadjoint operators to begin with is, well, they appear in physics, also in quantum mechanics in various situations. So one of the most popular ones would be simply scattering theory or scattering systems, where we have sort of a finite system and a sort of wave that comes from infinities, briefly interacts with our system and then sort of scatters away again. And in these systems, so to say, the long time behavior of our quantum particle would be described by the sort of resonance poles or the quantum resonances of our system, which can be described as actual like complex valued eigenvalues of some non-selfadjoint operator. Also, another nice physical system where they appear as open quantum systems, where you essentially have some sort of large quantum system and a smaller quantum system, which is kind of connected to the larger one. And so they have a sort of energy sink towards the larger one. And if you want to describe the effective dynamics of the sort of smaller quantum systems, this is usually done via these Lindblad operators, which are de facto non-selfadjoint operators, kind of reflected in the fact that you have this energy loss to the larger quantum system. Or simply damped systems, like you can think of the damped wave equation, or more fundamentally in PDEs, it appears in solvability theory or questions of stability of nonlinear PDEs in hydrodynamics, for example. So non-selfadjoint operators in the spectra are really interesting all around the place. So let me just give a sort of brief, what's the problem with these non-selfadjoint operators, or one of the problems is simply that they are spectrally unstable, meaning that you have very bad resolvent control in general. So meaning that the norm of the resolvent is not controlled anymore by the distance of the spectral parameter to the spectrum, as is the case in the self-adjoint case or the emission case, if you want to. So meaning that for these non-self-adjoint guys, the norm can be really extremely large, even when you're far away from the spectrum. So, and the direct consequence, which is now called this sort of pseudospectral effect, is simply that the spectrum of these guys, these non-self-adjoint operators, can be extremely unstable, even if you add a tiny, tiny perturbation. So it's maybe then normal that the sort of first interest for the spectral instability comes from numerical analysis, because there it's sort of poses extreme problems if you cannot trust your calculations anymore. And so one of the works around Treffer-10 in numerical analysis came up with this notion of epsilon pseudospectrum, which is simply for a epsilon positive, so positive epsilon you add to the spectrum of the operator itself. You add all the points where the norm of the resolvent is larger than 1 over epsilon. And so for self-adjoint guys, this simply means that you add disks of size epsilon around to your spectrum. So you blow it up a little bit by disks of size epsilon. But for non-self-adjoint operators, this can really mean that you're adding a huge part of the resolvent set. And so simply to give you a little bit of flavor, this notion is completely equivalent to this notion of spectral instability. So every point in the pseudospectrum essentially can be attained by a perturbation of size epsilon to your operator. So by the spectrum of a perturbation of size epsilon to your operator. And again, it's if you're in the pseudospectrum, another definition which is equivalent is simply that you have these quasimodes. So meaning that either you're already in the spectrum or you have some sort of mode that is an approximate eigenvector to Z, and the error is at most epsilon. So there you see this sort of epsilon reappearing again. And I mean, in various works recently, not only numerical analysis, but also nonlinear PDE or PDE, the sort of shift, there was a shift. So usually people studied the spectrum to say something about stability for solutions to nonlinear PDEs. But there was some recent works by, well, Swarovski and Raphael, Stansted and Gankowski, which showed actually that the pseudospectrum can be much more determining to if you have stability or not. So this is just this notion of spectral instability. So, but what does this talk about? Let's just jump a little for an example. So the easiest non-selfadjoint operator would be simply the Jordan block. So as this Topless matrix, we have ones in the first upper diagonal. So its spectrum is simply 0. But if you add a small noise, like in this case with a small coupling constant, 1 over the dimension to the power of n, and you add a sort of complex Gaussian random matrix, so from the Ginebra ensemble, then first we start out with the spectrum simply in 0. But if you add this perturbation, so the blue dots are now the perturbed spectrum, the spectrum immediately moves away from the original spectrum here at 0 to the unit circle. So you add a tiny perturbation and the spectrum moves a lot, which you do not have for self-adjoint problems simply due to spectral stability. But in this sort of non-self-adjoint case, the spectrum moves drastically, even though you had a tiny perturbation. So we're going to look at, in this talk, at the spectral asymptotics for noisy non-self-adjoint semiclassical pseudodifferential operators. So pseudodifferential operators for which we add a small noise term. The same for Topless matrices. And then we look at what happens, well, to the eigenvectors. So after we looked at the spectral asymptotics. So the first part will be the case where the unperturbed operator is simply a non-self-adjoint semiclassical pseudodifferential operator. So what does that mean? I'll be looking simply at the while quantization. So the unperturbed operator pH will be given by the sort of while quantization of a symbol. So we have a symbol here that is simply a smooth function on here. My phase space is R2D. To keep it simple, but it could be simply, if you're working on a manifold, it can be simply the cotangent space of the manifold. And here is a weight function. So this weight function is positive and grows at most polynomially quickly. So meaning here, this symbol is a good symbol for us if it is smooth, and all its derivatives are kind of controlled by this weight function. So they grow at most polynomially. Then I can define my pseudodifferential operator here simply as the quantization denoted by op of the symbol p applied to some function u as the sort of double. You take the double semiclassical Fourier transform essentially, and on the Fourier side you multiply by the symbol that has been essentially here symmetrized with respect to the position variable, and you apply it here to u. And so this is the symmetry here is due since we're taking the while quantization, but essentially you could take any other sort of pseudo-differential quantization that you like. So we simply will always require the p is an elliptic operator, so meaning that there is some z out for us such that p rho, so rho is in our phase space, minus z is sort of satisfies the symbol estimate, so meaning that it is lower bound by our controlling weight function. In this case, well, I mean, this pseudodifferential operator defines a nice continuous map from the Schwarz distributions to themselves, and also an unbounded operator on L2 space. And so we'll be studying, so in case there is any purely discrete spectrum of our operator, we'll be studying that, that sort of will keep that omega as inside the sort of discrete regime. And so a nice example to have in mind would be simply the non-self-adjoint harmonic oscillator, so where you have sort of the Laplacian h squared plus the complex valued potential, so I times x squared as on L2. And so this quantization sort of say relates the symbol of that operator in this case, so the Laplacian, semiclassical Laplacian becomes psi squared, so the frequency is squared, and the potential here Ix is simply remains the same. And here the phase space is simply R2D, and x psi, or sometimes written as rho, is a variable in phase space. And so the semiclassical machinery essentially gives us nice access to a symbolic calculus. So surely you've seen it. So essentially, for example, the commutator of our operator. Essentially, the commutator is the quantization of the Poisson bracket, so the on phase space here on R2D. So essentially, if I divide 1 over 2h, the commutator of pH star, so it's adjoint with itself, is in first order in h in our semiclassical parameter. So h, I should have written it somewhere, is, you should think of it as a small positive parameter. Okay, so h, and we'll be interested in h going to 0. And so in this quantization, essentially in first order in h, the quantization of the Poisson bracket of the real and imaginary part of our symbol gives us the commutator of the adjoint and with its of the operator with itself. And so since we're interested in non-selfadjoint operators, a very strong assumption, but a somehow very natural that we can make is that we want that the Poisson bracket of the real and imaginary part of our symbol is non-zero on the energy shells, essentially. The inverse image of some point Z, where we're interested to study the spectrum under the symbol or simply the principal symbol of our operator. Okay, so if this is the non-zero, then essentially we know that the commutator is non-zero, and we're definitely in the non-selfadjoint regime. So why is that an important relation even, or what's the connection to the pseudospectrum? So what we'll be interested in is this, what we call the zone of spectral instability, essentially is the image, the numerical image of our symbol on phase space and the closure. So that will be always noted by sigma. If we're outside of sigma, so in a complex plane, then there essentially we are spectrally stable, simply due to the usual pseudodifferential calculus. We have that the norm is somehow controlled by a constant. So if we're adding a small perturbation, something with coupling size small, so small in powers of h, and a small perturbation compared to the original operator, then the spectrum of this guy is definitely included in, well, a small neighborhood somehow that goes to this sigma range as h goes to 0. But why is that actually the zone of spectral instability, or why is that interesting? It's simply because we can construct quasimodes there. And so essentially remember that if we have good quasimodes, then we know, or we have a quasimode of an error epsilon, so meaning some mode E plus that is an sort of an approximate solution to this eigenvalue problem with an error epsilon. Here it's an H infinity error. Then we are definitely in the epsilon pseudospectrum. And there is an old result, or there's a result by, well, let's sort of say, was refound by Davies in '99 for Schrödinger operators with complex valued potentials, which goes back to Hermanda somehow in the PDE solvability theory, and then was refined by various people, so Bolton, Denker-Shastran-Swirsky, and also Pravda-Starov. But this result essentially tells you that if you have a point in phase space on this energy shell, where this Poisson bracket is negative, so if the real and imaginary part at this point is negative, then you can construct simply by a WKB construction a quasimode that is micro-localized to this point. So in position and in frequency away from this point, it decays faster than any power of h. So it is really, in a sense, localized in position and in frequency to a point. So essentially, you can think of it as a coherent state. You can construct this quasimode that is an h error infinity. And similar, if the Poisson bracket at this point rho minus is positive, then you have an quasimode for the adjoint problem. And so this means that if we have this sort of this Poisson bracket being non-zero, we're definitely in the H infinity pseudospectrum of our operator, and meaning that any perturbation of size, arbitrarily large size of H, can suffice to create spectrum in this zone. Okay. So maybe if I just go back to this example, so in this case, for this non-harmonic oscillator, the pseudospectrum sigma would be simply the right upper quadrant in C, whereas the spectrum of this guy is on a line, just on a line that is kind of shifted, discrete spectrum on a line turned up from by an angle of pi4. So we see the pseudospectral effect once more. So the question is, what does this sort of look like for generic perturbation? And for that, we use random perturbations. So we'll be looking mostly, so you can imagine two types if you want to, like, which would be either a random potential, so say a random combination of sort of modes EJ, that, for example, you take in some orthonormal basis of L2, or simply say the Fourier modes if you take on if you're working on L2S1, or you could also envision the Fourier modes in L2 RD, but simply then with some cutoff. So in any case, we construct a sort of random potential by a random linear combination where these random variables, if we're taking potential, to keep it simple, you should think of complex valued random variables which are independent and identically distributed and whose probability distribution has some Lebesgue density. So probably the density is not 100% necessary, but it is definitely current results needed. Whereas if you perturb with a sort of random matrix, in this case, we simply sort of take again our basis, we project on it and multiply it. So we create a matrix with respect to the spaces, and as coefficients, we use IID, complex valued random variables, which should at least satisfy sort of a 4-moment condition. So of expectation 0, variance 1, and the fourth, little bit more than the 4th moment. So a tiny epsilon 0 should be bounded. So some rather general random perturbations. So in this case, so what we're interested in is, well, what happens to the spectrum of our guy if we if we add now a tiny perturbation, and the coupling constant can even go up to being exponentially small in h, up to a sufficiently large power of h. So the power here on the upper bound will play a role, but for the beginning, we'll just think of it as being sufficiently large, and sufficiently large in the sense that the norm of the perturbation coupled with delta, so the coupling constant times this perturbation here, is smaller than 1 with high probability. So what happens? So a result going back to Hager and then Hager-Sjöstrand basically tells us that there is a while law. So if we perturb our operator with this arbitrarily small in powers of h perturbation, then the spectrum of the operator in the discrete, where the spectrum of the operator is discrete, suddenly satisfies a while law, even though it is non-selfadjoint. So let me just say, what is this while law? It tells us that if we count, so here it is an example operator, so simply h dx. I use the same notation as Peter in his previous talk, so d being 1 over I ddx plus some complex valued potential on L2S1 and h small parameter. If you, in this numerical simulation, you say the unperturbed spectrum is simply discrete h times z on the real line. But if you add a perturbation here, a small perturbation, it explodes away again from the original spectrum, and we count eigenvalues in a set omega. And there it satisfies a while law. So meaning that the spectral asymptotics goes like 1 over h to the power of d times the volume. So in a sense, we take the push forward under our symbol of the symplectic volume in phase space, and we integrate that against omega. With a small arrow here, I mean, we have precise error estimates with probability close to 1, but I didn't give you all the details here. So essentially, the interesting thing is, I mean, while laws definitely hold usually for self-adjoint pseudodifferential, semiclassical pseudodifferential operators in a very general setting. But as soon as you pass to non-self-adjoint guys, it doesn't hold at all anymore, especially when they're analytic pseudodifferential operators, for example. Usually have a sort of spectral localized on some curves, and you're far away from this sort of equidistribution. But the clue is essentially if you add an arbitrarily small perturbation with good probability, you get again your while law, even though it's non-self-adjoint. So this result has been extended in various cases. So first it goes back to Hager for model operator. Sjöstrand and Hager proved it for rather general pseudodifferential operators on RD, both perturbed with random matrices. And then also it was proven for non-semiclassical differential operators. Some recent work shows it also for Topless Quantization. So I'm gonna go a bit into, give you an example later on what these guys are. And there was also some related work by probabilists. And for if you perturb just with a random potential, you need an additional symmetry assumption on your symbol. You still remain non-self-adjoint, but you kind of have to reduce a little bit the symbol class you're looking at simply by that the frequency is so the symbol remains invariant under change of sign in frequency. And also, the general case was also done by Sjöstrand again. And for some analysis of the spectral statistics, so on the local scale, there was work of Stefan Nonmacher and myself, which shows that there is a sort of universality emerging. But I'm not going to go into detail for the spectral asymptotic for the spectral statistics today. So let me just go give you another example for this Topless quantization. So essentially, Topless quantization means that, well, so the symbol, so this is a bit of a lowbrow approach. So if essentially a function is a smooth function of the two even-dimensional torus, then you can represent the Topless quantization as the pseudo-differential operator, the while quantization, restricted to distributions which are periodic in position and in phase in frequency, which under certain conditions on H become discrete and finite dimensional spaces. And in this case, you can represent the operator by a matrix, actually, which has this usually tuplet structure. So here the symbol is just cosine of x and I cosine of psi, being position and frequency on the two-dimensional torus. And the difference is with the usual tuplet matrices is that you can allow for the function, the band structure. You have this usual band structure as in tuplets matrices, but now there can be functions on these bands which slightly vary. Okay, and in this example, we see again the unperturbed operator has this sort of nice spectral structure, and therefore it's called the Scottish flag operator because, well, you see the Scottish flag. But once you add a tiny perturbation again, so again a random matrix here, the spectrum blows up and essentially tries to fill this sort of region of spectral instability. Okay, so the range of the torus under the principal symbol. Okay, there was also recent work by probabilists which took a completely different approach and just took an ad hoc definition of this sort of twisted tuplets matrices, as they call it. So you have a band structure and varying functions on them. They again identify a symbol with that. So that work was done by Bazak, Paquette, and Zaitouni. And they get, again, you see sort of this sort of spectral, after a small random perturbation, the spectra starts filling sort of a compact space in the complex plane, and they get again a while law, but in a sort of weaker sense, so just by counting the eigenvalues and normalizing it by 1/n. So this counting measure here of the perturbed eigenvalues converges weakly in probability to again the push forward measure of what you would expect sorry, it should be not the Lebesgue measure on the circle here, but on the torus, sorry, arrow. But essentially they prove the same thing. Yes?
I have a question. If the symbol is complex,
yes,
wouldn't be the right side quantity complex? The push forward.
Which? Yes, this is a complex measure. Yes, right. But you see, it's a measure on C.
Ah, okay. Sorry, because the eigenvalues are also.
Yeah, the eigenvalues are complex. Right. Thank you. Yeah, exactly. Good clarification. So this is a complex measure. But it's completely reminiscent of the usual while law, so where you take a sort of the measure on phase space essentially and push it forward, the symplectic measure on phase space, and you push it forward by the symbol, which now is complex. So you get a measure on C. Exactly. So this would be a case of tuplets matrix where the bands are constant, and we'll get back to that a little bit later. So let me just describe a little bit. Sorry, was that all you wanted to know? Okay.
Thank you.
Thanks for the question. So let me just briefly describe a little bit the methods or the structure behind it, which is first is rather algebraic. So so there are various ways of studying this, and so this is one way of looking at it, which is I think a very robust way. So first of all, if we're looking at, well, pseudo-differential operators, with the discrete spectrum of pseudo-differential operators, then essentially we're interested in a Fredholm problem of index 0, right? And so to study that, I mean, first simply we regularize to pass to a bounded operator simply by constructing a symbol that is elliptic and that is differs from our original symbol by simply a compactly supported smooth function, such that the inverse is bijective, so that the quantization of our kind of deformed symbol is minus z is bijective in the region where we want to study the eigenvalues of the original operator. And then we simply regularize our originally perturbed operator by this sort of resultant here, which gives us 1 plus some trace class operator, which now we can study. And the the spectrum of these two guys here is exactly the same, since we simply regularized. So the first thing that we want to do is actually look at the singular values and the singular vectors of this operator here. So this regularized version. So, and if the unperturbed operator, and it's really the fact that these singular values and singular vectors are fundamental to the whole idea. So we take so what E1 to EM will be simply an orthonormal system of eigenvectors of PHZ star PHZ. Okay, so the singular vectors of PHZ associated to these eigenvalues, so of this self-adjoint problem here, T1 squared to Tm squared, that are sufficiently small, so very small for some alpha that is small but still larger than some constant over H. Okay, and due to the Fredholminess and index 0, essentially we know that there is this discrete spectrum here for the singular values. And so similar, we take for the sort of the formally adjoint, or the sort of on the quotations adjoint problem, where we take PHZ star. Okay, and F1, Fm are the eigenvectors corresponding to the same eigenvalues, because those guys have the same spectrum, but different eigenvectors, of course. With the F1, Fm are the eigenvectors of this guy corresponding to these singular values. And simply here, because this is a self-adjoint pseudo-differential problem, we have powerful machines of the pseudo-differential semiclassical machinery, and we get a nice control of the number of small singular values. Essentially, this is a while law for pseudo-differential operators. So if alpha is small, you see approaching H. Essentially here we go to H to the 1 minus D, so we're definitely below the while law count. Or essentially, it's a very precise while law, let's say it like this. So the next step is we set up a Grushin problem, which is a sort of auxiliary problem for our operator. So the key idea is essentially here you extend your problem, your operator that you wish to study, by 2 operators. Okay, those are both trace class. So R minus, essentially what it does, it projects onto the singular vectors for this PH star. And R plus, which we put here, essentially projects onto the singular vectors for PH star PH. Okay? So what you do here is simply, in this case, since we have Fredholm index 0, you add something that covers the co-kernel, and here you add something that covers the kernel of your operator. So since this is Fredholm of index 0, we are definitely invertible with an inverse, this E calligraphic, which we write by E plus, E minus plus, respecting the same structure here of this 2x2 matrix. So this Grushin problem essentially goes back to Grushin's work in the 70s for hypoelliptic pseudo-differential operators, and then also Chestrand in a different context, 73, and this particular choice for Hager-Chestrand in 2008. So the funny thing now is that since if we pick delta to be sufficiently small that invert this sort of random perturbation in norm times this operator here, which is also a bounded operator, still sufficiently small, the whole thing remains invertible if we simply replace the perturbed operator or the unperturbed operator here with the perturbed one. Okay, so now we can study the unperturbed one. And why do we do this is simply, so this is true, this is still invertible with high probability, but the fundamental key idea is why do we do this is simply the Schur complement formula. Because by Schur complement, we know that this guy here is invertible if and only if this guy is invertible. So the E minus plus, which is a finite dimensional matrix. Okay, so a CM matrix. And the key is simply that, well, you have a difficult infinite dimensional problem, and you revert it to, well, studying the spectrum. It's not really the spectrum, it's studying when is Z such that E minus plus has a kernel. Okay, so when it is not invertible. And so there is a bit of a trade-off. It's not linear anymore in Z, but at least it is finite dimensional, and this helps a lot. So simply then by using a bit of Fredholm determinants, we can study the log determinant of our operator of interest, who carries the information of its spectrum, which is simply given by the log determinant of the entire Grushin problem plus the log determinant of this guy here. Okay, so this is what we've gained. So why is that interesting? And simply, if you take the Laplacian of the log determinant, and so simply here I see this as a measure locally in C where we have discrete spectrum. Okay, so there where we have discrete spectrum, taking the Laplacian of the log of that determinant gives us the Dirac masses on the spectrum of the perturbed operator. Okay, so taking the Laplacian of this log determinant here and here. So essentially, we've passed to a self-adjoint problem in a sense, because here taking the modulus of the determinant of that essentially is the determinant of this matrix times its adjoint, and the same for this guy. So essentially, in a sense, you've passed to a self-adjoint problem, and that is a method in random matrix theory also referred to as hermitization, which goes back to Jirkov. But there are some problems, and let me just first show why this is practical. So by semiclassical analysis, essentially, well, I mean, simply by perturbative arguments, the perturbed Grushin problem, the log determinant of the perturbed Grushin problem is essentially the one up to a very small error of the unperturbed one. And since we've done everything in a sense by adding these R plus and R minus operators, we've essentially killed the small singular values. So this guy here is essentially the log determinant of pH star pH, so the self-adjoint matrix. So all the counting all the singular values, plus here alpha times some cutoff function chi, which is say 1 in the neighborhood of 0, of this, again, this self-adjoint operator divided by alpha, which, what does this guy do? This simply adds 1 times alpha when you are in the region of small singular values, okay? So this essentially lifts the spectrum of this operator here by something positive. And then doing a little bit more semiclassical or the simple sort of functional calculus and pseudo-differential calculus, you get a nice expression, so to say, for this log determinant, which is simply 1 over hd, 2 pi floating around, integral over phase space of the log of the principal symbol of this guy here, which is p rho minus z squared. So I've ignored in this case that here actually there was a normalization by resolvent. It's really not important. So essentially there would this floating around, but here you get why this is interesting, because if we take the Laplacian now, so you would take the Laplacian of this guy, and if you take the Laplacian of this guy now, you see that this is exactly the logarithmic potential of the measure from the while law. Okay, so you see this guy here actually has already the information that we need. Contains the while law, but so what does this guy do? So actually this can create only problems. So this is actually the reason why we need a random perturbation, because so the determinant of this E minus plus unperturbed version is just the product of all the smallest singular values of our operator. And since here we actually see the pseudospectral effect. Remember, for non-selfadjoint operators, you can have an extremely large pseudospectrum. So you can have a lot of extremely small singular values. And so here, actually, by taking the log determinant of the unperturbed one, and you can have an escape of mass to 0. So essentially, the reason why we wouldn't have a while law for the unperturbed operator, as we see here by the exclusion problem, is simply because this guy, due to the pseudospectral effect, gives us an escape of mass to 0. However, in comes, so to say, the random perturbation, which saves us. And the reason is simply that in general, random matrices have a way smaller pseudospectrum than non-deterministic operators. It's simply that, so if, for example, you take a random matrix with IID entries, which is sub-Gaussian, or say a Gaussian random matrix, then the probability that the norm, so here I normalized my random matrix by 1 over square root of n minus z, so z is a fixed spectral parameter in complex plane. So the norm of the resolvent here, that this is larger than 1 over epsilon, so remembering the definition of the pseudospectrum, is bounded by n times epsilon plus something exponentially small in n. Okay, so there was a lot of recent work also in the random matrix community. I mean, this sort of works go originally back to Spielmann and Teng, Sanka, Spielmann and Teng, Rudolfson and Vershinin and Tao and Wu and Cook, and all in these works, it's similar results, but always for a more general class of random matrices. And so essentially, this tells us that in expectation, if we take the Lebesgue measure of the pseudospectrum of such a random matrix, it is n times epsilon up to that small error. So even if epsilon is very small, essentially it's not as large as you would get it for a deterministic operator, but still it is not as good as for a normal operator, so or self-adjoint operator, where the size of the pseudospectrum is typically of size epsilon squared, coming from simply this, the spectral theorem. So how do we now prove these results on the while law? This is simply, well, essentially you perform a a bit of an intricate version of Jensen's formula, right? So you're interested in counting the zeros of this holomorphic function here, the det of this perturbed operator. So you need to upper bound the log determinant by something. You also need to lower bound the log determinant by something, and then essentially by Jensen's formula, you get a good estimate on the counting on the number of zeros. So the idea is simply that we take this formula here for the log potential, for the log determinants of our operator by the Grushin problem. I mean, this is the dominant term, which we know to be this by semiclassical analysis. The non-dominant term, bounding it from above, is trivial simply because it is a bounded small operator, so we can somehow get a small arrow term. But the lower bound on this sort of function where we need to count the zeros is more tricky, and there comes in this random perturbation. So it's simply that by this random perturbation, by simply saying that, well, this sort of random matrices have a small pseudospectrum, we get that the log determinant of the E minus plus, which is essentially a deterministic matrix plus a random matrix, is not too small with good probability. Okay, and that saves us so that we get the corresponding lower bound here. And now essentially by using a very refined version of counting zeros of holomorphic functions due to Hager and Chestrand, we get that the number of eigenvalues of the perturbed problem in omega has the leading asymptotics given by this while law, essentially, with good probability, because here you lose probability, essentially. Okay, so now let's, actually, may I quickly ask, until when is my time now?
You started 5 minutes after the scheduled time, so I guess we finished 5 minutes after, so that would be another 5 minutes.
Okay, so originally I forgot, but okay, I'll just carry on. So let me just briefly go over this. So the same holds true essentially for non-selfadjoint Topless matrices. So I put this in because there was a Topless discussion this morning also. So if you do the same thing for Topless matrices, you have a symbol for these Topless matrices with coefficients which are in L1. So the 1 over zeta in C star, essentially being e to the minus I xi, would be quantized by the Fourier transform to the powers of the left shift operator or the right shift operator. And then by restricting this to finite intervals on ZD, so 0 to n, you get a nice Topless matrix, so the usual with a fixed band structure. So I skipped this. Maybe there's a lot of stuff known about the spectra of these matrices, but let me just skip this. But in a sense, here we get another while law, which is due to some work with Chestrand. So the same holds true. Here there is the image of the principal symbol. So this curve here is the image under S1 of our symbol of the Topless matrix. Inside you see the spectrum of the unperturbed matrix. Okay, and once we add a tiny perturbation, the spectrum again tries to follow the PS1, so the image of the range of the principal symbol. And you have again sort of this Y law here. What was 1 over H before is now N, so simply the dimension of the matrix going to infinity. But you have again this sort of push forward of the corresponding measure on the unit circle by the principal symbol with good probability. There was a lot of work by probabilists, by Bazak, Paquette, and Zaitouni, which showed a similar thing in a sort of weaker form by simply the convergence of the empirical spectral measure to the same thing here in probability. And just for the Jordan block, there was a lot of work actually by probabilists before. By the first work by Chniadi in 2002, which used the heavy machinery of free probability, and then Bordenave and Capitaine in similar settings, Davis, Hager, and Guillaume, Wood, and Zaitouni, which all had this sort of showed the similar phenomenon, but completely different methods. So let me just end the discussion maybe by looking at what happens with eigenvectors. Okay, so again, let's go back to the Jordan block. Okay, easy case, Jordan block, 1 on the upper diagonal. So there's one eigenvector, and for the spectrum of 0, it's 1, 0, 0. But how do the eigenvectors look like once we add a perturbation? And that is actually very interesting, because instead of having a peak of 1 and 0 and then 0 everywhere, the eigenvectors start spreading out like this. Okay, so gamma here it will be interesting, because gamma is the power here, the negative power of the perturbation coupling constant. And we have to be slightly larger than 1 over square root of n to actually be still in the regime of small perturbations. So in a sense, the larger this is starting to spread out the eigenvectors. But actually, there is a sort of transition phenomenon. So for gamma larger than 1, they in a sense are still localized. Okay, they have this sort of slow tails, but they're still localized to either left or the right sides. But once we hit 1, we're still in a small perturbation, so we're not in the sort of regime where the random matrix takes over. They start to become delocalized, and between 1, this gamma, so gamma again was the power of 1 over n. So once the coupling constant is larger than 1 over n, but still smaller than 1 over square root of n, they become more and more delocalized in a sense, and until here, when gamma is really larger than 1 over square root of n, we are in the random matrix regime, and they're completely delocalized. Okay, so let me just simply give you an overview of what happens. We go back to the Grushin problem, which is simply this algebraic construction. And the important thing here is the following, that now we focus on the vector E plus delta. So this matrix here, which is a bijection between the kernel of E minus plus delta, so this sort of effective Hamiltonian, and the matrix that we're interested to study, the spectrum. So meaning that this sends a kernel element of this guy to an eigenvector of this guy. And we can show essentially that if we look at an asymptotic expansion of this guy, that the leading order, I mean, with high probability, the rest you can say it goes to 0 with n goes to infinity, but the leading order is just a projection on the singular vectors of the unperturbed operator. And so essentially the eigenvectors of the perturbed matrix are given with high probability by a random linear combination of the singular vectors of the unperturbed operator. Okay, and the random coefficients here are the kernel elements of this matrix. Okay, so this is I mean, then if you really want to know precise information, you have to do a lot of additional work to study the kernel elements of this guy. But there you can use random matrix techniques to study sort of how do they look like? Are they delocalized or not? And on the other hand, you need to study with either pseudodifferential techniques or other analytic techniques how do the singular vectors of the unperturbed matrix look like? And the Grushin problem, in a sense, gives you this nice combination or this nice bridge between the two worlds. And so I'll skip a little bit here. I put a little bit in the techniques, how to do it, but let me just end by citing this result. So together with Bazak and Saitouni, we've shown essentially that the eigenvectors localize. So if you can allow me to call this still localizing. And so here in the regime where the tuplets matrix is perturbed by, say, we can allow for a very large class of random matrices, but the coupling constant is still larger than 1. So we can only describe the region here where they, in a sense, are localized. We're currently doing the work for the sort of after this delocalization phenomenon, but the current theorem only has that gamma is larger than 1. And in this case, we can show that the eigenvectors, so we're taking an eigenvalue of this perturbed matrix with a corresponding eigenvector, and we can show that it localizes on the scale of n over log n. Okay, n is the dimension of the matrix. So what we can show is with probability going to 1 as n goes to infinity, if L is in the discrete interval of 1 to n, then so if you look at the L2 norm of the eigenvector from L, so could be large, could be small, to n, it behaves like this, e to the power of minus CL log n over n. So if L is very close to 1, then you simply get nothing here. This is just order 1. But so after L is n over log n, then you start seeing an exponential decay here, which we see here on this tail. Okay, and this holds when the winding number of the eigenvalue of the symbol curve, right? So we had the symbol curve around the eigenvalue is positive. Simply when it is negative, instead of being localized on the left side, it is localized on the right side. This is connected to the theorem that we saw today by Francesca. Due to the first sort of index theorem for tuplets matrices. This is simply reminiscent of that. And just, sorry, we're drawing a little bit, but to finish, sort of there needs to be this corresponding lower bound to actually say that they are localized on the scale. So essentially saying that here the probability is not as good as in the first statement, but so you fix any eta positive but small, and then we have the statement with probability larger than 1 minus eta. Okay. So with this probability in a sort of uniformity in eigenvalues, so it is uniform in eigenvalues in disks, for eigenvalues in disks that are of size log n over n. If you look at the localization behavior of the eigenvector in the L2 norm from L to L prime, which both are smaller than n over log n, but are different, are at a distance of slightly larger than 1 over square root of n, then this L2 mass of the eigenvector is larger than L prime minus L log n over n, okay, for with the positive winding number. And this similar statement just simply localized from the right instead of the left for negative winding number. Okay, and so here is a picture again. So some eigenvalue here for the perturbed matrix gives you this eigenvector. And so, well, simply lots of work to do. Just an outlook. If you go as a coupling constant larger than 1, then the eigenvalues are not contained anymore inside a region of fixed winding number, but they start bleeding out into a different region of different winding number, right? Because here there is winding number 1, here there is winding number 2. And this essentially, and some other phenomenon will essentially lead to a sort of more delocalized phenomenon, and we conjectured currently that this can be described by a nice Gaussian process. Okay, so that was it. Thank you very much. Sorry for overdrawing a little bit, and thank you for your attention.
Well, thank you very much for that fascinating talk. I guess we have time for a few questions before a quick break and then on with the discussion, which might be room for more questions. But does anyone have a question that they'd like to ask now? Alexander?
So in this context, you know that transition happens at gamma equal to 1/2?
Yes. So in the context of these Topless matrices, essentially, we know that the transition happens at gamma equal to 1/2. Yes. Let me go up here. Yeah.
And so how do you know that?
Essentially, what happens is we can look at the Gaussian problem. Okay. Essentially, the reason in the transition is this m here. Okay. So what we know is the following. So how best to describe this is simply that if for this Gaussian problem to be invertible, okay, for delta large, so if delta is smaller than 1, this Gaussian problem here is invertible with m finite. And essentially what you take is here, how to explain this best, there is the important thing, m is essentially determined by the number of singular values that you have that are smaller than some alpha here, right? And to have, if delta is larger or gamma is larger than 1, the alpha that you can take to keep this invertible determines you that m is finite and essentially given by the index of the operator, which is due to the fact that in this case there is a spectral gap of the singular values. So this the t squared winding number, and the next one, the t squared, where m is winding number plus 1. For z, for z being an eigenvalue. So the reason we can do this is twofold. Actually, here you can see it in this picture. So when gamma is larger or equal to 1, the eigenvalues stay inside a fixed region of a fixed winding number. They do not cross over. This is in a sense because the perturbation is not strong enough for them to cross into a different region of different winding number. Whereas if the perturbation is stronger than 1, then they have, as you can see in the sort of in this picture here, then they start bleeding over. So eigenvalues from one side start bleeding over into a region of different winding number. So even here, the winding number would be 0, but actually the perturbation is strong enough so that eigenvalues start bleeding out there. Okay, and what this tells you is that if you look at the singular values for these